how this C++ feature can make your code 16 times slower. Just yesterday, my friend said to me, "My computer is so outdated, I need this new part, this new part." But modern hardware is extremely fast. It's just software slow. Most developers are either lazy, uneducated, or don't care to make performance software. When you see one of them pass, you can just ha 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 laugh at them. So you really don't want to be like them. That's why today you're gonna learn what is operator equal, how it works, what's the problem with it, some interesting benchmarks, dives into assembly, and a surprising fix. So in most programming languages, when you say variable equals something, what happens? For example, in C, you can have like a structure with a string in it, with a array of some numbers, and maybe like a floating point number. Okay, so when you say equals, when you write equals, this string, it's just one integer, it's a pointer. This is just a pointer, and this is just one floating point number. So essentially just copy one integer, one integer, one integer. And no matter how long the string will be, it will be turned into just one pointer, one integer. All you do when you say a equals this thing is you copy 3 integers. 364 bits. And if you talk about garbage collected languages, then it's even simpler. No matter what the size of this value is, you just copy one pointer. But in C++, something wonderful happens. Let me show you. Look at this code. It's quite a simple code. So you have a structure, which is like, you have a map of cities, vector of cities. City has a name, whether it borders an ocean, and an array of indices of the neighboring cities. Okay, and this function, you give it a map, you give it a city, and it just looks for the neighbors, whether any of them border an ocean. And if any of them border an ocean, okay, here's the name of the city. Quite a simple function, right? But there's a landmine in it. What do you think it is? So you remember I was talking about the assignment, right? The wonderful thing is, in C++, the developers of standard library, of the developers of vector, they thought, you know, when you have like an integer and you copy it, when you change the copy, the original integer doesn't change. So it is called the value semantics. And vectors, which are dynamic arrays, vectors in C++ also obey this value semantics. When you assign them, when you change the copy, the original value doesn't change. Isn't it just great? So it implies when you make an assignment of vector, it makes new memory, it allocates new array, it copies all of the elements. And then it needs to also deallocate this copy when you're done with it. Isn't it just wonderful, huh? So this is what happens in here. When you say ct equals this creates a whole new array, allocates memory, copies elements. Then, at the end of the loop, it deallocates them. Oh! And how can we fix it? Well, easily, right? You just use a pointer or a reference. I mean, it's not a real fix, because it's quite ugly. And I will tell you what's the better fix a bit later. But right now, why should I care? Why should you care about it? Like, sure, why not just copy the whole array? It will work correctly, right? Well, obviously, you use more memory. And not just that, it's slower. It's very much slower. Before that, let me tell you a story. One day, developer at Google thought, Why don't we look at the how the Chrome browser deals with memory? They ran through all the allocations and whatever and discovered that on every key stroke, Chrome made 25,000 allocations. Just one keystroke, 25,000 allocations. Moreover, if you look at all of the allocations, half of them were made by strings. You remember that funny class std string? Yeah. So, the point is value semantics, allowing binding function of any complexity to an equal operator is insanity. And I could have shown you an example where I just iterate through all of the cities and just like this thing would be also copying, allocating memory, copying. If you don't put this wonderful reference thing, it will be making copies as well. Obviously, you really don't want to be making so many allocations. Like, remember the 25,000 allocation of every keystroke? No wonder Chrome is so memory hungry. So let me show you how slow this code is. So I benchmarked the slow version and it runs at about 10-15 nanoseconds on my machine. Now I benchmarked the fast version and it runs at about 55 nanoseconds on my machine. Pretty stark, pretty big difference. If you're tired of the C++ surprises, want to write actually performance software, and go beyond those simple tricks, check the top link in the description. I will teach you the best knowledge I've accumulated over many years of writing performance software. But now, the big insight is, in C++ you have a vector, which is not really a vector, it's not a mathematical vector, it's just a crazy bad name. But I implemented a simple dynamic array. It has just three fields: data, length, capacity. Nothing crazy in the code, just super basic implementation. And I can use the dynamic array, my dynamic array, instead of the standard vector. What do you think will happen in the slow version of the function if I use just the dynamic array? Well, look, I'm gonna spoil it to you. There is no operator equal, or you may say that the default operator equal, the only thing it does is copy those three fields and nothing else. It's a shallow copy. And we can see what will be the performance difference between those two functions, whether I use the reference or the shallow copy. What do you think is going to be faster? I benchmarked the shallow copy with the slow version of the code, and we're getting almost the same performance, about like 70 nanoseconds. Very fascinating. And it's quite obvious to guess that if I ran the fast version of this code, no matter whether the operator equal is deep or shallow, we use the reference, so performance is about 55 nanoseconds. So the performance for the slow but shallow copy version is almost the same. What C++ does is deep copy. What C does is shallow copy. So if you have any pointers to anything else, you just copy the pointer, you don't copy the data. This is shallow copy, and the deep copy is what you do, recursive copy of everything underneath. If you have an array, you copy every element and so on and so forth. I made a table so it's easier to understand what happened. Deep copy is very slow, and everything else is about 20 times faster than the deep copy. The deep reference, shallow reference, they're essentially the same code. But shallow copy is almost on par with the reference. It means the compiler can optimize the copies. It can say, huh, well, you don't need to load the whole thing. You can just load the fields that you actually need. You can even not care about the vector that we have in here, the neighbors, since we don't use it in this calculation. 20 times faster, that's significant. Think about it. Just using the correct data structure by default gives you an improvement in a simple code. You don't want a complicated code. You don't want a hard code which is hard to read and write and hard to think about. The simple code. And this 20 times faster is kind of arbitrary, since here in the vector which I was copying, I have just 9 elements of 64 bits. And it's like, imagine if there are more. So often it's handy, instead of guessing, to look at the assembly instructions generated from our code. So the things that your CPU executes. Here you have the assembly for the shallow copy, and here you have the assembly for deep copy. And you can just see that there are many more instructions for the deep copying. And you can see there are throws, deallocations, memory moves, allocations. So we kind of already know what the issue is just by looking at the assembly from the big picture. But oftentimes you need to actually dig deeper into the instructions to understand which version is faster and why. Luckily, not today. And the big problem is, this behavior is default one. You don't opt in, and you cannot really opt out. Instead, just use your own data structures. Make your own standard library. Don't be the culprit of the value semantics cult. Good languages prohibit you from making equal sign mean anything but a shallow copy of the bytes of the structure. And it's very important to have good default behaviors, because most of the developers will not go out of their way to make their code more complicated just to achieve something. If you can make default behavior good, this is golden. Some people say, well, just reflexively always delete your operator equals and copy constructors. But it's copium. It's not a real solution, it's a band-aid. In the same way as just using references in an optimized code, it requires additional code, additional consideration. It pollutes your head with more ideas. It makes it harder to write software. You need to trench through more shit. That's why it's not a good solution. Good solution is to never, ever use value semantics. And the potential solution is to even switch to another language, which actually respects developers who try to write performance software. Write reliable and performant code. Check the top link in the description. Bye.